So, we have seen the difference between reducible and irreducible representations. Now, we are going to prove we are going to use a theorem called the great orthogonality theorem, and this will help us construct what is known as the character table of the group. Okay. So, in order to introduce the great orthogonality theorem, I will start with a few notations. Okay. So, suppose you have a group, the order of the group so you have a group of symmetry operations okay. The operations denoted by R okay. So, R can be any symmetry operation of the group. The order of the group we will use H to denote the order of the group. So, if it is a group of order 10, then H will be 10. If it is a group of order 3, H will be 3. We will use the symbol gamma I R M N. Okay. So, this is a symbol that is used to, this is the M cross N matrix element of ith irreducible representation of R. Okay. So, this is the central object in the great orthogonality theorem. Now, gamma I of R M n represents the m cross nth matrix element of the ith irreducible representation of R. Okay. So, just to tell you what this means, this let us look at the irreducible representation. So, irreducible representation corresponds to a matrix. Okay. So, you have a matrix corresponding to an irreducible representation, you have a matrix for every operation in the group. Okay. So, irreducible this is matrix. So, matrix for each operation in group. Okay. So, for the ith irreducible representation, you will have a matrix for R, you have a matrix for all the element for all the symmetry operations, but you also have for R. Okay. So, now you look at the matrix for R. So, if you look at R and you look at the m cross nth element. So, you look at the mth row and the nth column and you look at this element. So, this is gamma I R M n. Okay. So, this is one particular matrix element. So, this whole thing is a scalar, one element of a matrix. Okay. So, it is just one particular element of a matrix. Okay. So, now if you take a different irreducible representation, I will have a different matrix gamma j r m n. Okay. And now, the great orthogonality theorem is quite a remarkable theorem. We will write down the theorem soon, but basically what it tells you is that these various matrices corresponding to different irreducible representations and corresponding to different elements. Okay. So, they share some special properties. Okay. So, let us you have matrices for different operations. Okay. You have matrices for different each operation in different representations okay. So, you can have different matrices for different operations and different matrices for each operation in a different representation, it will be a different matrix, and I want to emphasize that all these representations need not have the same dimensionality. So, there might be one representation which is a 2 by 2 matrix, another might be a 3 by 3 matrix, a third might be a 1 by 1 matrix, and all these matrices. So, the great orthogonality theorem states okay. So, we will write it in the following form: sum over R gamma I of R m n gamma j of R n prime. Okay. So, you look at the same matrix element in two different representations. So, I and j are different representations. So, these are different irreducible representations. So, you look at the matrix corresponding to the same element in different irreducible representations, and here you look at the m nth element, here you look at the m prime n prime element, okay, and you sum this over all the operations. So, these are sum over all operations of okay. And when you do this, what you will find is quite a remarkable orthogonality, and so I will write this in a form, and then so I will write it as H, where H is the order of the group, divided by square root of L I L j, okay, and I will explain what L I and L j are, times delta I j delta m m prime n n prime. Okay. Now, L I and L j, they refer to dimensionality, dimension of irreducible representation, and I will use the symbol IR for irreducible representation. Okay. So, L I is the dimensionality of the ith irreducible representation, L j is the dimensionality of the jth irreducible representation. So, what it means is that corresponding to each irreducible representation, you have a matrix, and the size of that matrix is what L I is. Okay. So, the size of the matrix for the ith irreducible representation is L I, the size of the matrix for the jth irreducible representation is L j. Okay. And I have written it in this form. So, it looks completely symmetric to changing I and j, m and m prime, n and m prime. So, it is a completely symmetric result. Okay. And notice that it says that so each one of these looks like an orthogonality relation. Okay. It says that m has to be equal to m prime, n has to be equal to n prime, I has to be equal to j. If these conditions are not satisfied, then the right hand side is 0. Okay. So, it is each of these looks like an orthogonality relation. So, it looks, so that is why this whole thing is called a great orthogonality relation. In fact, it is a product of these three orthogonality relations. Okay. So, this is 0 unless I equal to j. Okay. This is 0 unless m equal to m prime, this is 0 unless n equal to n prime, all these three should be satisfied. Okay. And this, so if I equal to j, m and m prime are the same, n and n prime are the same, then this is just h over L I, this is it is just equal to h over L I. Okay. This is if I equal to j, m equal to m prime, n equal to n prime. Okay. Now, this is a matrix element. Okay. So, there is no restriction on this. This can be real, it can be integer, it can be a fraction, it can be complex, it can be negative, it can be anything. However, Li has to be an integer. H also obviously has to be an integer, since this is a dimension, this is the order of the group. So, both of these have to be integers. Okay. So, so notice that this relation gives it looks very abstract, and it does not look very practical, but once we unfurl this, what we will do is we will break this up into a series of relations, and then we will demonstrate the practicality of these relations. So, we can write this in the following form. We can say that suppose all these are the same, I m n are equal to j m prime n prime, then you can write this as sum over r gamma I of r m n gamma I of r. This should be a complex conjugate. Should be a gamma I r m n star. This is equal to h by L I. Okay. So, now you can see that that you are taking the mnth element, okay, and you are just taking gamma I into gamma I star. Okay. So, we are just squaring the matrix element for a particular operation. Okay. So, we are squaring the matrix element for a particular operation, and we are summing over all operations. Okay. So, essentially we are taking the same matrix element, okay, and we are squaring it over all particular operations, and that gives you h divided by Li. Okay. So, we will keep this, and then we will start trying to show how you can use this practically. Before that, I just want to tell you where we are trying to go with all this. Okay. So, why are we interested in the great orthogonality theorem, and what is the significance? Okay. So, the goal of GOT is to derive character table of a group. Okay. So, in other words, we want to actually work out what the character table of any group is. If you look at if you look at the character table of any group, for example, if you look at C3V, okay, C3V. Now, this has, if you see the character table in any book, you will see this as E, there is 2C, 2C3 and 3 sigma. Okay. So, you will find something like this 3 sigma, okay. And then you will see something like this A1, A2 and E. Okay. And what you will find, I will show only part of the character table. So, you will find 1 1 1, 1 1 minus 1, then you will find 2 minus 1 0. Okay. So, what you find here in the character table, these are the classes, no, these are the irreducible representations. And these are the classes. Okay. So, what we say is that C3 has 3 classes, the identity element is in a class. There are 2 elements in this class C3, and there are 3 elements in class sigma. Okay. 3 elements belong to a class. And then what are these numbers? This number is nothing but the character. Okay. Now, the character is also the trace. So, I will say trace or character of class in irreducible representation. So, it is in this. So, this refers to the character of sigma, Okay, so any element, all these three elements, since they belong to the same class, they have the same character. So this is the character of sigma in this A1. So character of sigma, which is the element of the class in A1, okay, or if you want, you can write 3 sigma. Okay, since all these three sigmas have the same character, so you just need to write the typical character of 1. Okay. So, so this is what the character table contains, and now the kind of things we want to know is how many such irreducible representations are there. How many such irreducible representations can you have? What should be their characters? Okay, so these are the things that we want to find out, and we want to work them out. And what you will find is that the great orthogonality theorem gives you a good method to work out all these details. Okay, so now it turns out that the great orthogonality theorem in this form, I already said that it is a great orthogonality theorem in the sense there are many orthogonality relations in it. Okay, so suppose I fix m and n, okay, then I can do I can get an orthogonality relation that involves I and j. Suppose I fix I and j to some value, then I will get an orthogonality relation involving m and n. Okay, so this gives you many different orthogonality relations, and what we will do is to construct some very practical some relations that can be used in a very practical way using these orthogonality relations. Okay. So these are the consequences of great orthogonality theorem. Okay, I will use the symbol GOT for this. Okay. Now let's look at this. This is the dimensionality of an irreducible representation. Okay, Li refers to the dimensionality of an irreducible representation. Okay. Now you can easily see that if I sum over all irreducible representations and I sum over the dimensionalities of the irreducible representations, squared dimensionalities of the irreducible representations. Okay. So, sum of squares of the dimensionalities of the irreducible representation, this is equal to h. So, this is equal to h. This is actually not so easy to prove. Okay, this turns out to be not so easy to prove. However, you can easily show that this is relatively easier to show. This is relatively easier to show, but to show this is slightly more difficult. So, actually this follows in quite a straightforward way, but to go from here to this relation is not as straightforward. Okay. Now, the dimensionality, this is the dimensionality of ith irreducible representation, okay, and you are summing over all the possible irreducible representations. So, sum over all irreducible representations. Okay. So, now the dimensionality of the ith irreducible representation is nothing but the character of the identity in the ith irreducible representation. So, the identity element just has one along the diagonals. So, the trace of the identity is nothing but the dimensionality of the representation. Okay. So, the trace of the identity is the dimensionality of the representation. So, this is one consequence of the great orthogonality theorem, and once again I emphasize that I have not actually shown this. Okay. This is not as easy to show. Okay. It is relatively easier to show something like this, okay. But doing this other thing, other part is not as easy to show. Okay. Now, the second relation is the following. Sum over all operations chi I of r square is equal to H. Okay, so this is another relation. Notice that that out here we had one particular matrix element. So, gamma I corresponds to one element of the matrix, whereas chi refers to the trace of the same matrix. Okay. So, gamma I mn is the mnth element, chi I is the trace of the matrix. So, chi I of R is nothing but sum over I gamma I sum over j, or I will say sum over m gamma I R m m. Okay, so, sum over the diagonal elements. So, chi I of R is nothing but this. Okay. And so what this relation says is that if I take chi I star chi I, okay, that is like taking the complex conjugate of this and multiplying it by itself, and if you work it out, you will get this is equal to H. Sorry, this is sum over all the operations, sum over all the operations. Okay, so this is and this actually directly follows from the great orthogonality theorem. So, you can just substitute this value, okay, and you can let us see what happens if we substitute this value. So, left hand side. So, proof is left hand side is equal to sum over R, okay. Then you have sum over m gamma I of R m m, okay, that is chi I of R, and chi I R square is nothing but chi I R into chi I R star sum over n, just to differentiate it from m, okay, this gamma I of R n n star. Okay, so, this is nothing but this, okay. And if you change the order, you can say you have sum over m, sum over n. So, so you get sum over R, sum over m, and sum over n. Okay, so I take the sum over n outside, and what I will get is okay. And now I can switch the order. I can take the sum over R inside. So, if I take the sum over R inside, then I use the GOT. Okay. So, if I take the sum over R, I use the GOT, okay, then I will get okay. So, then I will get a delta mn, okay, I will get a delta mn, and that will allow me to get rid of one of these sums. So, all I will be left with is sum over m, and mm, okay. All I will have is gamma I of R m m. Okay. So, if I use the great orthogonality theorem here, then what I will get is sum over m, sum over n. Okay. Then I have the sum over R, gamma I R star. Okay. So, that will give me delta m n, okay, and delta m n into delta m n. So, we will get it twice into H by L I. So, that is what I have. So, now I can write this as so h by L I, and this is just equal to. So, I can do the sum over n. If I do the sum over n, it will just go away. So, I will just get sum over m h by L I. Okay. And now, sum over m, okay, sum over m, and this is just a constant, this is independent of m. So, this is just, so sum over m will just give me a factor of L I, okay, because I am just summing over all the rows of the matrix, and the number of rows is equal to L I. Okay, so, this is just equal to H. Okay, so we showed this relation. This relation follows directly from the GOT. Okay, so the proof is complete. So this is equal to right hand side. Okay. So the important step is right here, that the sum over m of a constant. Okay, so the number of m goes from 1 to L I. Okay, so sum over m is just L I, and this completes the proof. Okay. So, this is an extremely useful relation, because now this relates the characters of the irreducible the characters of the operations. Okay. And notice it is the characters of the operations that appear in the character table. Okay. So, this is a very useful representation, a very useful relation. So, this and this will turn out to be two of the most useful relations that we will use. Okay. And then we'll mention two more things. The third consequence is that sum over R, chi I of R, chi j of R equal to 0. Okay. This again follows directly from the great orthogonality theorem. Now, obviously, all I said if two R's belong to the same class, they will have the same trace. Okay. So, two R's belonging to the same class have the same trace in that particular representations. Okay. So we will mention this, all elements belonging to a class have same character in any irreducible representation. So, you look at any irreducible representation, and the elements belonging to the same class will have the same character. Okay. So, the last useful thing is that the number of classes is equal to number of irreducible representations. Okay. So, the number of classes in a group is equal to the number of irreducible representation. This is sometimes called the class equation in algebra. So, in abstract algebra, this is sometimes called a class equation. Now, this is again this you can immediately see that this is extremely useful and very practical relation. Okay. The number of classes is equal to number of irreducible representation. Notice it does not say that the dimensionality of the classes and the dimensionality of irreducible representations are the same. All it says is that the number of classes you have in any group should be equal to the number of irreducible representations. Okay. So these 5 relations, okay, these 5 consequences of the great orthogonality theorem are extremely useful practically. So, these are the ones. What we want to find out is what are the dimensionalities of the irreducible representations and what are their characters. So, we want to find out all the Li's and the chi i's, chi I of R. Okay. So now what we are going to do is we will look at some examples where we use this information to derive the character table of various groups. Okay. So, let us take an example. and we will take the group C2V. Okay, so let us take C2V. Now, C2V has the following has an identity. It has a C2, it has a sigma V and a sigma V prime. So, it has only 4 operations, okay, 4 operations, and each of these is in their own class. So, it has 4 classes. So, then C2V looks like this: E C2 sigma V sigma V prime. So, there are 4 elements, and there are 4 classes. Okay. So, we have to find the irreducible representation. So, now you can immediately see that the number of irreducible. So, I will just write down what are the various things we are using. So, since 4 classes imply 4 irreducible representations, okay, and we will just call them gamma 1, gamma 2, gamma 3, gamma 4. So, we denote as gamma 1, okay. Now, we need to determine the dimensionality of each of these. Okay, you need to determine the dimensionality of each of these. So, gamma 1 with dimensions L1, L2, L3, L4. Okay, so we just assume that they are, you just denote them by L1, L2, L3, L4. Now, first thing you will say is that L1 square plus L2 square plus L3 square plus L4 square is equal to H, and H is equal to 4. Okay. Now, L1, L2, L3 and L4 have to be non-zero integers, non-zero positive integers. So, this implies L1 equal to L2 equal to L3 equal to L4 equal to 1. Okay. So, these have to be positive integers. So, immediately you can say that that is the only possibility. So, therefore, each of these are one dimensional representations. So, we conclude that each of these is a one dimensional representation. Okay. Then we use the relation that we can use the relation that sum over all operations chi I of r star okay, sum of the traces has to be equal to H. Equal to 4. Okay. So, now what should be the character of identity in each of the representations? That should just be equal to the dimensionality. So, since we have chi I of E is equal to Li is equal to 1. Okay, so, you can immediately say that this should be 1 here. Okay. And for each of the others, okay, so you can have each of so the squares of the remaining characters should add up to 3. Okay, so, squares of the remaining characters should add up to 3. Okay, so squares of character of this and this should add up to 3. Okay. So, suppose you choose chi I of C2 square plus chi I of sigma V square plus chi I of sigma V prime square equal to 3. Okay. And the additional relation is your orthogonality relation. Okay. The other the additional relation is the orthogonality relation, which says that chi I of r chi j of r sum over r is equal to 0 if I not equal to j. Okay. So, for two different representations they should be orthogonal to each other. Okay. So, now you can clearly see how I mean this will end up giving you sufficient conditions to derive all the characters. You can see that one will be what is called the trivial representation. So, we had already seen that each of these can be represented by 1, then the products are preserved. Okay. Now, the other representations should be such that if I multiply these two and add all of them up, I should get 0. Okay. So, I already have 1 here. So, if I multiply these two and these two, I should get and add them up, I should get -1. Okay. So, one way to satisfy this is to put 2 of them to be -1 and 1 to be 1. Okay. So, suppose I put 1 here -1 -1. Okay. Then or else I can do -1 1 -1, or I can do -1 -1 1. Okay. So, now you clearly see that if I multiply these two, okay, if I take if I take a dot product of these two vectors, okay, which is essentially this condition. Okay. So, if I take chi I, if I have to sum over R, so I sum over all these. Okay. So, it is this into this plus this into this plus this into this plus this into this, clearly it gives me 0. Similarly, if I take these two, I will get 0. If I take these two, I will get 0. Okay. Now, what about these two? Suppose I take these two, what do I get? 1 into 1 is 1, -1 into -1 is 1, 1 into -1 is -1, 1 into -1 is -1. So, I get +2 and -2, they cancel, I get 0. So, basically these 4 gammas looked at as vectors are mutually orthogonal. Okay. So, this turns out to be the character of this character table of this group. Okay. So, you need so we will use both these results in the following way. Okay. Now, you can also show that these are the only possible representations. Okay. It is not hard to show that these are the only possible representations, and in fact, that is not a very difficult exercise to show. Okay. So, so overall I think this illustrates the power of this method. Okay, the power of the great orthogonality theorem. Okay, now I just want to make a connection with the multiplication table. So, what you have is you have the character table and you have the multiplication table. Okay, so you have E C2 sigma v prime, and you have E prime. So, if I take these two, E times E is E prime, v prime sigma v C2 sigma v prime sigma v C2. Okay, so this is the multiplication table, and now let's look at the character table. So, you have E C2 sigma v prime. Now, you have gamma 1, gamma 2, gamma 3, gamma 4. Okay, so the trivial representation is 1 1 1 1. Then you have 1 1 minus 1 minus 1, 1 minus 1 1 minus 1, and 1 minus 1 minus 1 1. Okay. So, I deliberately wrote it in this order. So, I have 1s along the diagonals, that just looks like I have identity along the diagonals. Okay. Then I have this okay. So, I have minus 1s here, and okay, and I have minus 1s here. Okay. Okay, I have minus 1s in this region. Okay. Now, notice that what you have is C2 is same as here. So, it is like minus 1 that is here. sigma v is same as here, sigma v prime is here. Okay. So you can see that this sort of anti-symmetry is built in this also. Okay. So, basically the product of operations, suppose I take C 2 times sigma v, okay, then I get sigma v prime. Okay. Now, if I take any representation, okay, so if I take any representation, so let us say I take this representation, I multiply the character of C 2, multiply the character of sigma v, I should get the character of sigma v prime, and indeed this is true. I multiply minus 1 by 1, I get minus 1, 1 times minus 1 I get minus 1, 1 times 1 I get 1, minus 1 times minus 1 I get 1. Okay. So, this multiplicative property of the group is preserved in the character table. Okay. So, the character table basically gives you all this information. Okay. So, the same information is given here. Now, in this case the character table, since each of the representations was one dimensional, okay, and each of the classes just had one elements. Okay. So, the character table looks just like a multiplication table. Okay. So, the character table and multiplication table look identical. Next we will look at an example where the character table and multiplication table look a little different. So, let us take the group C 3 V. Okay. This has the order of this group is 6. Okay. So, H equal to 6. Okay. It has 3 classes, it has E, 2 C 3 and 3 sigma. Okay. So, it has 3 classes. Okay. And now we have to work out the character table of this group. Okay. So, the character table will look like this: E, 2 C 3, 3 sigma. Okay. Now, the number of irreducible representations has to be 3. So, we can just say gamma 1, gamma 2, gamma 3. Okay. Now, you can say that L 1 square plus L 2 square plus L 3 square equal to 6. Okay. So, this is a condition that has to be satisfied. So, if L 1, so the only way this is at only possibility L 1 equal to L 2 equal to 1, L 3 equal to 2. Okay. And actually you can always switch the numbers, but basically 2 of them have to be 1 and 1 has to be 2. Okay. So, the 2 that are 1 you call L 1 and L 2, the one that is 2 you call it L 3. Okay. So, that is the only possibility. So, you have a one dimensional representation, this is also a one dimensional representation, and this is a two dimensional representation. Okay. Now you can work out the character of identity. Identity will be 1, 1 and 2. Okay. So, the character of identity is this. Okay. Now, you will always have what is called the trivial representation. So, where both these will be 1. Okay. So, this is called the trivial representation, and this will always be one of the possible representations. Okay. So, where the character of everything is 1, because then the multiplication and all the products are preserved. Okay. So, now what you want is two other representations. Okay. So, let us try to determine them. We will use the So, let us look at this representation. So, for gamma 2, in gamma 2, okay, chi of E square plus, now there are two operations in C 3. Okay. So, we are using sum over R chi I of R square equal to H. Okay. So, chi of E square plus 2. So, there are two operations in C 3, each of them have in class C 3, each of them have the same character, plus 3 chi of sigma square, this is equal to 6. Okay. Now, chi E square is just 1. So, this implies 2 chi 3 or chi C 3 square plus 3 chi C2 square is equal to 5. Okay. Now, the squares have to be positive. Okay. So, the squares have to be positive, okay. They cannot be negative, okay. And moreover you have the property that this should be orthogonal to this, okay. So, also we have, so for gamma 1 gamma 2, okay. So, for gamma 1 and gamma 2 we have chi. So, character of identity in this multiplied by character of identity in this. So, that is 1 plus character of C 3 in this. So, you have twice chi C 3, okay. Character of C 3 in this is just 1 plus 3 chi sigma equal to 0, okay. So, this should be satisfied, and you can immediately see that that there are two ways of satisfying both these relations, okay. So, the squares of you can this plus this can be equal to minus of this. So, you can have so chi C 3 equal to 1, chi sigma equal to minus 1. Okay. So, this satisfies both these relations, because their squares will automatically, this square is equal to 1, this square is equal to 1. So, the sum of 2 times this square plus 3 times this square is 5. Similarly, this is equal to 1. So, 1 plus 2 is 3 and this is minus 3. So, you get 0. Okay. So, this is one method that works. Okay. Now, and you can easily show that based on this orthogonality, this is the only thing that can work. What about this? What about this condition? So, how do you determine these two? Okay. So, let us look at. So, in gamma 3. So, in gamma 3 we have chi of E square is 4 plus 2 chi of C 3 square plus 3 chi C 2 or sigma square is equal to 6. So, this implies twice chi C 3 square plus thrice chi sigma square equal to 2. Okay. And the other condition, the orthogonality condition, will say that this is 2. So, 2 plus twice chi C 3 plus thrice chi sigma equal to 0. Okay. So, twice this plus 3 times this should be minus 2, whereas twice square of this plus thrice square of this should be equal to 2, and you can easily see that this is satisfied with chi C 3 equal to 1, chi sigma equal to 0. Okay. So, clearly this is satisfied with chi C 3 equal to 1 and chi sigma equal to 0. So, chi C 3 equal to minus 1, sorry, minus 1. So, if this is minus 1, this minus this will, this 2 plus minus 2 gives 0, and this is 0. So, it does not affect. So, what we conclude is that this should be minus 1 and this should be 0, and these are the 3 irreducible representations, and these are the characters of the representations. So, we constructed the character table of a group that is non-trivial, okay, and these are in fact all the irreducible representations that you can do. These are the whatever if you generate a 2-dimensional irreducible representation, these will be the characters, okay. And if you generate the 1-dimensional irreducible representation, the characters can be this or this, okay. So, so now we have seen how to construct the basic character table. What we will do next is two things. One is how how to express a reducible representation in terms of irreducible representations, and then we will go to the actual character table that is seen in most of your books.